Hey, this is Mr. Ariel. I'm here today with a lesson for gas laws. Now, first up, there's a lot of things you probably already know about gases, like gases take the shape and volume of their container. They're highly compressible, and they'll mix evenly if you mix them up in the same container. And last, gases have very low densities when you compare them with a liquid or a solid. Now, we're going to learn a few more things about gases in this class, and all of it revolves around this idea called the kinetic molecular theory. This idea can describe the motion and nature of gas particles, but it has 5 assumptions. First up, we assume that the particles in a gas are extremely small. Basically, we assume that their size is completely negligible. That means it doesn't matter at all, and we just think of them as single points moving around in a container. Next up, we assume that gas particles are in constant random motion, and they're going to move in straight lines until they collide with each other or the walls of their container. Like here in this balloon, we have a blown up section, and here's one particle of gas hitting the side of the balloon and bouncing off of it. The third assumption is that gas particles neither attract nor repel each other. And then the fourth assumption is the average kinetic energy of the molecules is proportional to the temperatures of the particles measured in Kelvin. We'll talk more about the Kelvin temperature scale in just a minute, but I'm going to add this idea out here right now, that a higher temperature is going to be equal to more kinetic energy. That's what that term is proportional means. If you increase the temperature, you've increased the kinetic energy. Now that fifth assumption is that gas pressures come from the collisions of the particles with the walls of the container. Back to the balloon example, that balloon is inflated because those particles of gas are hitting the side of the container, the wall of the balloon, and bouncing off of it. And that's what gives gas its pressure. Now, if you got all those ideas, let's go ahead and move on to the next page. And this page is mostly review, but there are 4 key variables to consider when talking about gases. We have pressure, volume, temperature, and the number of moles. Now, we're going to spend some time talking about pressure because it's a new quantity in this class. We haven't dealt with it before. But the other ones are pretty straightforward, like volume measures the space something occupies, and we've been dealing with liters and milliliters for the entire course. Temperature is also something you probably have a lot of experience with. The technical definition is that it measures the average kinetic energy of the particles, and I'm sure you've used a thermometer at some point in your life. Now in the box on the right, I definitely want you to get some notes about the Kelvin scale. We use it for gas law calculations because 0 degrees Kelvin is the point called absolute zero. All particle motion will come to a stop. Even those gas particles bouncing around in that balloon in the previous example, even those particles will stop moving completely. Now, a curious thing about the Kelvin scale is you actually don't write a degree sign like I just put in. I drew it in to show you that's not the letters OK. Let me take it back out now. The point I need you to get here is that 0 degrees Kelvin is the same thing as negative 273 degrees Celsius. That's pretty cold, and in Fahrenheit, that's almost negative 460 degrees. Now I want you to add in 2 notes about why we use the Kelvin temperature scale for chemistry. First up, it gets rid of negative values in calculations, and you'll see this issue crop up when we start doing some calculations. You'll get a negative value for something, and you'll think there's no way that value could ever be negative in real life. And so the Kelvin temperature scale helps us deal with that by having all positive numbers. The second reason for the Kelvin scale is scaling issues. The example I have for this is thinking about something that's 100 degrees Celsius, and it's a fact that it's not twice as hot as 50 degrees Celsius. I know 50 times 2 is 100, but if we convert both of these temperatures to Kelvin, 100 degrees Celsius is 373 degrees Kelvin. We have the formula right here in your notes. It's already written for you. So 100 degrees Celsius is 373 Kelvin, but 50 degrees Celsius is 323 Kelvin. So for this temperature over here to be twice as hot, that would have to be 323 Kelvin multiplied by 2, and that works out to be 646 Kelvin. Or to put that back into Celsius, that's 373 degrees Celsius. Now jumping back up here to pressure, that's definitely a new quantity for us in chemistry. The technical definition is that it measures the force per unit area. Like if you think about massaging a really sore muscle, you can apply a lot of force over a very small area with the tips of your finger, and that pressure you exert can help you feel better. Now, one thing about pressure in chemistry is there are a lot of different units that can be used to measure pressure. And all of these different measurements that we have for pressure, We have them because there were a lot of different ways that people figured out how to measure pressure. Nowadays, we can just use a pressure sensor, but we do need to step back in time a little bit and figure out how a barometer and a manometer work, because they were some of the old school ways of measuring pressure. So moving on to the next slide. Over here on the left is a barometer, and this is just a tube of glass, and it's completely sealed at the top. Nothing can get in or out, and it's a vacuum, meaning all of the gas has been removed from this section of the tube. This dish down here is filled with a liquid, and traditionally it was filled with mercury, and the way it works is air pressure, that's abbreviated PATM. Well, air pressure will push down on the dish of mercury, causing that mercury to then rise up into the tube. Air pressure all around you is not something you can really sense with your body because we've all adapted to it, but you know that it's there because when you go up in an airplane or you drive up a steep mountain road, your ears definitely respond to the lack of air pressure at that elevation. Now this H abbreviated right here is the height of the column of mercury, and 1 atmosphere of pressure is equal to 760 millimeters of mercury. That's how far up the mercury will be driven by 1 atmosphere of air pressure. So again, the barometer is a way to measure air pressure, but there's also a device called a manometer. Now this is a closed-ended manometer, and what that means is this top of the tube right here is completely shut. And then our gas sample is contained inside of a chamber, and what's happening here is you know that gas is exerting a pressure on all parts of the container, pushing it outward. So that also means that gas pressure pushes through the tube and ultimately pushes whatever liquid is here, it pushes that liquid down enough to make it rise up, and that height can be measured. And just like that barometer, this section up here is a complete vacuum. There's nothing in that part of the tube at all. So for the barometer and the closed-ended manometer, the formulas are the same. The gas pressure is equal to the height of that liquid that is being pushed up the tube. Now for an open-ended manometer, it's a little bit different. I'm sure you can figure out open-ended means that tube is not shut. And so here, again, that gas pressure is pushing out on all parts of the container, and it's pushing down this tube. But notice that the height of the liquid is actually higher on the left-hand side, and that's because the pressure of the atmosphere itself is pushing that liquid down in the tube and compressing this gas somewhat. So definitely get this part into your notes, that this formula right here is for when the pressure of the gas is less than the pressure of the atmosphere. And then the formula on the right, I'm going to cross that part out and put it here so it's a little bit easier to read. But this entire formula is for when the pressure of the gas is greater than the pressure of the atmosphere. And you can see that here, that gas pressure is pushing out on all sides of the container, down through the tube, and pushing that liquid up on the other side. For perspective, if the gas pressure and the atmospheric pressure were the exact same, then that level of the liquid would be the same on both sides. Now we've got a few more things down at the bottom of this page, so let me move that up. We have 2 formulas on this page and then 2 on the next. The first one is Boyle's Law, and it relates pressure and volume. And this part of the table right here, we're not going to use it an awful lot, but I'll talk about it real quick right now. Boyle's Law says that the pressure and the volume, if you multiply them together for a gas, they would equal K, and that's just a constant. And again, we're not going to use this equation very much, but it is useful to get the idea of how these variables are related. For example, if you were to increase the pressure, I'm drawing an arrow upward, if you increase the pressure on a gas, that will cause its volume to decrease. Like if we had a pressure of 1 and a volume of 1, we could multiply those together and get a 1. But if we were to increase the pressure, let's say make it 2, well, now for this to all equal out to that constant of 1, this would have to be 0.5. And I usually think about this with arrows. It's an inverse relationship. And that means if we're increasing pressure, volume will decrease. Like our example, if you squeeze a sealed water bottle harder, that's higher pressure. That becomes more difficult as the volume decreases. Now the next law we're going to learn about is called Charles's Law. It relates volume and temperature. And again, volume divided by temperature is equal to a constant. But this is a direct relationship. For example, if we were to decrease the temperature of something, that's going to cause its volume to decrease as well, in order for it to all work out to be the same constant on the other side. A good example for this one is taking a balloon outside in the cold. If it's perfectly inflated inside, but you take it outside on a very cold day or even throw it in the freezer, that will make it shrink somewhat, and it'll appear to be not quite as inflated. Now, last thing on the slide, I should have mentioned this equation on the previous example with Boyle's law, and then Charles's law. This is called a two-point equation, and we'll use it a lot in chemistry to compare the conditions of a gas under one condition, and then how they would change in a second condition. But there's nothing you really need to write there, so let's move on. All right, next up, we've got two more laws. There's Gay-Lussac's law. It relates pressure and temperature, and this is again a direct relationship. In our example here, the tire pressure decreases in the winter. That's because of that direct relationship. The temperature of the gas inside your tire decreases on a cold day. The pressure will decrease as well in order for that to remain a constant on the other side of the equation. Our last law we need to learn is Avogadro's law, and it relates volume and the number of moles. I'm not sure we've seen that abbreviation before, so I'm going to add it in, and I think you should too. Now, this relationship is direct, and I think it's the most common sense of all of them, because the example is when you put more air into a balloon, the balloon is going to get larger. And again, that's the direct relationship. You increase the number of moles, we're going to increase the volume in order to have a constant on the other side of the equation. Now, if you're stressing out over these four formulas, you're going to get a copy of the formula sheet on every quiz or test that you need it for. You don't have to memorize them, but after a while, you'll probably know most of them by heart. Now it's time to get into the practice. First up, I've got 2.5 liters of a gas. I'm going to make a note that that's volume, and we have that gas at 298 Kelvin, that's temperature, and we have another temperature, and we want to know what is the new volume of the gas. So the challenge of these problems at first is just finding which formula will help you, and for this, it's going to be Charles's law because we have volume and temperature. So if you were to flip back, you'd see that formula is V1 over T1 equals V2 over T2. And this is that two-point equation. We're using one side for one point in the problem and the other side for the other point in the problem. So now I can just plug in my numbers. We got V1 is 2.5 liters, and we want to know the new volume, so that's going to be V2. And our original temperature was 298 Kelvin, and our final temperature is 354 Kelvin. So to solve this, we can just cross multiply, and that would be V2 times 298 Kelvin, and if you actually multiply the 2.5 and the 354, that works out to 885, and those units are liters times Kelvin. So to finish up, we can just divide by 298, and of course that cancels out, and the Kelvin right here, that cancels out too. That'll leave us with a new volume of 2.97 liters. Now on the second problem, we have a volume and we have moles. And so that means we need to use Avogadro's law, and that's the one you can see on this screen. It's V1 over N1 equals V2 over N2. So our V1, that's 2 liters, and our N1, the number of moles, that's 1.75. And we want to know the new volume. What will the volume be? That's V2, and it's going to be over 2 moles being added to what we already have. So that's going to be 3.75 moles. So again, I'm going to cross multiply. So that's V2 times 1.75 moles, and 2 times 3.75, that works out to be 7.5 moles times liters. I'm going to divide through by 1.75 moles. Of course, it's going to cancel. 1.75 on this side. The moles will cancel, and when we do division, that works out to be 4.29 liters. All right, for the last one, we've got 5.10 liters. That's a volume, and we want to know the pressure of the gas. And so if you flip back on the sheet, you'll find Boyle's law. That's P1V1 equals P2V2. And so I'm going to start plugging in my numbers. Now my first pressure is 155 kPa, that's kilopascals, and our original volume is 5.10 liters, and that's going to be equal to our pressure 2, that's what we want to solve for, and the pressure is being decreased to 2.55 liters. So to solve this, I can just divide by 2.55. That all cancels out, and the liters cancel out. And when I finish up that math, P2 is going to work out to be 310 kilopascals. Now let me move the board a little bit so we can get down to the I do. For this, we're just going to convert the following pressures into the other units just to get you a little familiarity with them. So we want to go atmospheres to millimeters of mercury. Now these conversion factors that I'm about to use, they're back on a previous page of notes, and again, you get to have them on a formula sheet with you for a test, so don't stress out. So we're going to go atmospheres to millimeters of mercury, so this is just a dimensional analysis problem, I need atmospheres to be down here, and I need millimeters of mercury to be up here. And the rule is that 1 atmosphere is 760 millimeters of mercury. Now, atmospheres cancel out, and if you were to use a calculator, that'll come out to be 950 millimeters of mercury. To convert that to torr, the rule is that 760 millimeters of mercury, let me put it down here so it cancels correctly, well, that's equal to 760 torr. Remember, we have a lot of different units for pressure because there were a lot of different ways that it was measured, but these two happen to be almost equivalent except for their name. Now, if you do this math, it's not real difficult, don't even need a calculator, that's going to be 950 torr. And then moving that on to kilopascals, the conversion factor there is that 760 torr is equal to 101.3 kilopascals. So if that cancels and that cancels, and we plug those numbers into a calculator, that'll work out to be 126.63 kPa. Going kind of in the other direction, let's start with 705 torr. We can do that same calculation. 760 torr is equal to 101.3 kilopascals. Torrs cancel out. We can plug those numbers in a calculator, and that's going to be 93.97 kPa. Or if we want to go this way, back to millimeters of mercury, we can put torr here, millimeters of mercury up here. But remember, those are the same number for that one. And so that all cancels out. And so that's going to be 705 millimeters of mercury. And then one last one going this way, 705 millimeters of mercury. We can use that conversion factor that 760 millimeters of mercury is equal to 1 atmosphere of pressure. And so if we cancel our units and we plug those numbers in a calculator, that'll work out to be 0.93 atmospheres. All right, so that was the ID. We've got 2 more problems to go, so let me flip the page. Here we need to read the pressure of the gas for each of the following manometers. Notice this is the open-ended manometer, and so this atmospheric pressure is pushing down into the tube, causing that liquid to rise up and compress the gas. And we know that that height difference is 14.2 millimeters of mercury. And we're using the formula for where the gas pressure is less than the pressure of the atmosphere. That's why we're subtracting here. So the answer here is going to be the pressure of a gas is equal to the atmospheric pressure, that's 762 millimeters of mercury, minus that height, 14.2 millimeters of mercury. And so that'll work out to be 747.8 millimeters of mercury. Now for this closed-ended manometer over here, this is much easier because the formula for that says the pressure of a gas is equal to the pressure of that height right here. And so the answer on this one is just 30.8 millimeters of mercury. Remember that gas is exerting a pressure in all directions, and that includes down onto this liquid, causing the other side of it to rise up by this amount. All right, on this last problem, we want to figure out what is the pressure of a gas, and we know its temperature, and we knew its pressure and temperature at an earlier time. So pressure and temperature, that's Gay-Lussac's law. That's P1 over T1 is equal to P2 over T2. Again, don't stress out about these formulas. You're going to get a copy of them to use whenever you need them. So let's plug in our numbers. Pressure 1 is 805 millimeters of mercury, and that's over the temperature, and it's in 50 degrees Celsius, but we got to remember that's got to be in Kelvin. So 50 plus 273, that comes out to be 323 degree Kelvin. So I'm going to put that here, 323 Kelvin. Remember, you don't use a degree sign with Kelvin. And we want to know the pressure 2, and we want to know that at 325 Kelvin. If you remember, we use Kelvin to avoid the issue of having negatives in calculations. Here's a place where it's really going to show up. If this original number we had been given for temperature was actually a negative degrees Celsius, and we plugged it into the denominator here, we would end up getting a negative pressure, and that's not really a thing that exists in real life. And so we use Kelvin to avoid having negatives. So I'm going to finish this up and cross multiply. So we'll have P2 times 323 Kelvin. And if we multiply 805 times 325, that's 261,625 millimeters of mercury times Kelvin. And so we'll finish it up, divide by Kelvin on both sides. And of course the Kelvin will cancel out. And if we plug those numbers in a calculator, pressure 2 is going to be 809.98 millimeters of mercury. Well, if you made it this far, you're all the way to the end of the video. I hope it's been helpful to you today, and as always, thanks for watching.